Okay, so let's do some examples where we predict the molecular geometry of different molecules using valence shell electron pair repulsion theory. Let's start with CH4, also known as methane. So the first thing you have to do is use the handy hints to draw the best Lewis structure that you can for methane. If you need to, you can go back to chapter 3 and review how to draw Lewis structures. But the best Lewis structure and the only Lewis structure for methane is going to look like this: a carbon bonded to 4 hydrogens. Now, bear in mind, I'm drawing it in 2 dimensions, so it's quite deceptive. It looks like all of those bond angles are right angles, 90-degree angles. But molecules do not exist in 2 dimensions. They exist in 3 dimensions. So in reality, these bonds have more space than is implied by the 2 dimensional drawing. All of the bond angles are going to be 109.5 degrees, much larger than the 90 degrees that it appears to be in this 2 dimensional image. So this is because when we have a substituent number of 4 around that carbon, and we have no lone pairs, the geometry, according to our VSEPR theory handout, is going to be tetrahedral. So these 4 carbon atoms point to the corners of a tetrahedron in 3 dimensional space. All of the bond angles are 109.5 degrees in this perfect tetrahedron. Now let's do another one. Let's do Ni3, or nitrogen triiodide. First, I want to draw the Lewis structure. So I'm going to do this quickly. Obviously, you may need to go through the handy hints and do it in a bit more detail. Now I have 7 electrons brought by each iodine to the table, and then the nitrogen brings 5 electrons to the table. So in this molecule, in its Lewis structure, I can see that the nitrogen has a substituent number of 4 because I'm counting up each bond, 1, 2, 3, and then the lone pair, 4, to get 4 regions of electron density surrounding that nitrogen. So substituent number of 4 with 1 lone pair gives me a special kind of geometry called a trigonal pyramid. And you can see that if you look at the handout, where we're looking for a situation where the substituent number is 4 and I have 1 lone pair. So that would be kind of like this one, the trigonal pyramidal geometry. The bond angles are going to be like the bond angles in a tetrahedron, but slightly compressed because remember, the lone pair takes up more space than the bonding pairs. So both of these bond angles, okay, so the geometry is a trigonal pyramid. And both of the bond angles are going to be slightly less than 109.5 degrees. So remember up here in the perfect tetrahedron for CH4, all the bond angles are 109.5. In this molecule, Ni3, because the lone pair takes up more space than the bonding pairs, the bond angles are going to be slightly less than 109.5 because they're going to be compressed by that lone pair. All right, another example, SOF2. So I'm going to tell you that in this molecule, sulfur is the central atom. You can tell that because it is the most electropositive atom, and it's also the third row atom, so that gives you a hint about it being the central atom. Now, how am I going to organize the oxygens and the fluorine around it? You can draw its Lewis structure, and the best Lewis structure that you can draw for this molecule is going to have sulfur expanding its octet, because let's see, if I start spending all of the electrons that everybody is bringing to the table, I actually am going to end up with a lone pair on the sulfur atom. This is the best possible Lewis structure that I can draw because it's the one that reduces all 4 mole charges to 0. And sulfur doesn't mind having a dectet because it's a third row atom. So let's figure out the geometry of this structure and let's predict the bond angles. It has, the sulfur atom, rather, has a substituent number of 4 because I'm counting up each bond, 1, 2, 3, and then the lone pair counts as 4. So like the one above it, Ni3, this is a situation where I have a substituent number of 4 and then 1 lone pair. So the geometry is also going to be a trigonal pyramid for this one. Now, in this situation, if I'm trying to figure out the approximate bond angle, I have to remember that lone pairs take up the most space of all, followed by double bonds, followed by single bonds. So it's going to be a trigonal pyramid with uneven bond angles. The lone pair takes up the most space, and that means that all of the bond angles are going to be less than 109.5 degrees. And I would say that the bond angle of the fluorine sulfur to the oxygen is going to be still less than 109.5 degrees, but larger than the bond angle of the fluorine sulfur to fluorine. So another way of showing that is that the bond angle here is going to be just a little bit less than 109.5 degrees, and the bond angle here is going to be a little bit more or less than 109.5 degrees. But all of the bond angles will be around 109.5 degrees. They're just going to be compressed by the lone pair. So you've got to remember, lone pairs take up the most space, followed by multiple bonds, followed by single bonds.